In the previous video, I proved that the intersection n of all normal subgroups containing the subgroup H in a group G is the smallest normal subgroup of G containing H, and such n is often called the normal closure of H in G. This time I would like to talk about the intuition behind. Let f from G to G' be a homomorphism whose kernel contains H. Since the kernel of f is a normal subgroup of G, and n is the smallest normal subgroup of G containing H, the kernel of f contains n. And just like the kernel of f I mentioned in one of my past videos, there exists a unique homomorphism f star from G mod n to G', which is defined by the same rule as before, said to be induced by f, making the maps commutative with phi being the canonical map. However, this raises a question of what's the difference between this G mod n and the previously defined G mod kernel of f. In short, G mod kernel of f collapses all of the redundancy entirely based on what the homomorphism f can't distinguish, whereas G mod n also depends on the choice of the subgroup H resides in kernel of f. Then n is the minimal expansion of H to become normal in G, such that the quotient group G mod n can be constructed. Since n is contained in kernel of f, which makes the redundancy collapsing ability of G mod n weaker than G mod kernel of f. In other words, G mod n retains more information than G mod kernel of f. To understand it in a more concrete way, let's consider the relationship between the mathematical descriptions and the physical phenomenon. Previously, if I collapsed the redundancy entirely based on f, then regardless of whether it's because of gauge, translational, temporal, rotational, or other symmetries, those mathematical descriptions that can produce the same result would collapse to a single point in the quotient group, and an injective homomorphism would bring these points to the corresponding physical phenomenon. On the other hand, if I collapse the redundancy also based on the choice of the subgroup in the kernel, for example those that are only related by gauge symmetry, then more points would be generated in the quotient group, which retains other types of symmetry, and the homomorphism would no longer be injective. This means that with this normal closure of H in G, one has the freedom to filter the redundancy based on one's choice of subgroup H in kernel of f. Thus, normal closure is the minimal way to enforce that a chosen redundancy behaves well under group operations without discarding more information than necessary.